We've recently spent a lot of time looking at how we calculate the first derivative and the second derivative of a function. But a lot of questions involve relating those ideas of derivative to the graphs of the functions. So today we're going to look at how those different equations of the function, the derivative, and the second derivative actually relate to how the graph looks.
F of x equals x cubed plus 3x squared minus 9x minus 11. Now, based on the work that we've been doing in class lately, it's pretty easy to work out what the derivative and the second derivative of this function is going to be. Using the power rule, we can calculate that the derivative is going to be 3x squared plus 6x minus 9. Remember, this 11 disappears when we differentiate. Now, to find out the second derivative, we simply differentiate again. Again, bringing the power down the front and multiplying. 6x becomes 6, and this time the minus 9 disappears. So we can easily find the first derivative and the second derivative from the original function. These are pretty basic skills, but actually interpreting what these mean in relation to the graph is the hard part of the questions that you'll get in your exam. So we're going to look at each of these and what they show about a graph. And we're going to start off with the basic function and review what that shows about graphs.
And that we were interested in. And I've placed a point along the curve. And what I'm going to get to GeoGebra to do in a second is to calculate the function value based on where p is. So if I click this here, what GeoGebra has done to get this number 11.7 is it's taken the x coordinate of this point. So actually, if I moved it here, okay, the x coordinate would be -3. It's taken -3, substituted it into this equation, and it's come out with the number 16. Now, if I look at how that number, that result from that substitution, relates to where I am in the graph, I can notice a few things. All around this area, we notice that the number that I get out is positive. And this is indicating that the point P is above the x-axis. It's a positive value. Similarly, if I came right over here to the right-hand side, we'd see that in this area, that number is positive. If I take P below the x-axis to somewhere around here, we can see that the function value is negative. It's below the x-axis. So in this region here, we're getting all negative values of f of x. And over here, we're getting negative values of f of x. And that makes sense because this f of x, remember, is the y coordinate of p. Now, if I move p to somewhere like this, to one of my x-intercepts, and it doesn't want to grab it right there, I'll try this one here. If I move p right onto the x-axis, we see that f of x is equal to 0. And this is how we can determine where x-intercepts are, by thinking about the places where f of x is equal to 0. And there's going to be 3 of those places on this particular curve.
Name a word to describe what f of x tells us about the graph. That word would be height. The value of the function tells us the height of the curve at a particular point. So if I'm somewhere where the curve is above the x-axis, like here, then we expect f of x to have a value greater than 0, that is to be positive. So I have the curve above the x-axis when f of x is greater than 0. If I've got a situation like this, where I've got a point that's on the curve somewhere where it's below the x-axis, I expect to get a negative value because this point is a negative distance from the x-axis. So in this situation, we have f of x less than 0. Finally, if we take a point where the the graph is on the x-axis, that is if we're at an x-intercept, then we expect the function to have a value of 0. Tells us the height of a point on the curve. Let's now talk about what the first derivative tells us about the function at a particular location.
Of our function, what I'm going to do now is I'm actually going to draw in, as well as having the height of the function marked and calculated, I'm also going to draw in the tangent at that point P. And what I'm going to get GeoGebra to do is to evaluate the first derivative at that location. And if we remember our definition of the derivative, it was always categorizing the tangent, the gradient of the tangent at a particular location. So if we're somewhere around here on the curve, we can see that our tangent has a positive gradient. It's increasing from left to right. That's going to be the case anywhere on this left-hand side of the function. This first derivative is going to be always positive. That's also going to be the case on the right-hand side of the graph, somewhere over here. Okay? In this region, we have a positive gradient. The graph is going uphill from left to right. And that red tangent line has a positive gradient clearly. If I go somewhere between those two locations, somewhere in the middle here, we can see that all along here, the gradient is negative. We've got a negative value for the gradient of this tangent line. So that is what the first derivative tells us about a graph. It tells us about the slope of the graph at any particular location. Now, there are two places where this particular function is not going to be either positive or negative, and those two places are going to be here at this maximum point, or possibly over here at this minimum point. Now, this maximum and this minimum are examples of what we call stationary points. They're places where the first derivative is 0. Now, a lot of stationary points are either these maxima or minima, but there is a third option that we'll talk about later. But the key thing to take out of this demonstration is that when the first derivative is a positive number, it means this tangent line has a positive gradient. When it's a negative, then we have a negative gradient on the tangent line at that point. In other words, the curve is decreasing. And when the first derivative is equal to 0, we have a stationary point. And that's usually a maximum or a minimum.
A word to describe what the gradient is doing, I would say that it categorizes the slope of the graph. So in a situation like this one, where the tangent at that location is increasing, it has a positive slope, graph is increasing, then I would say that, then we expect that the first derivative will have a value bigger than 0. That is, we expect it to be positive. That tells us that we're increasing at that location. If we're in a situation like this, where the function is decreasing, the tangent has a negative gradient, then the first derivative is negative. And if we're in a situation like this, where we're at a place where the tangent is horizontal, we call these stationary points, then we expect the first derivative to be equal to 0.
About the function and how its value gives us the height of a particular point, and how the first derivative tells us about the slope at a particular location. We're going to talk about the second derivative and how it relates to the shape of the graph. And I've got a point P that's moving along the curve. This time though, instead of calculating the function value or the first derivative, I'm calculating the second derivative. So what I'm doing here, is I'm taking the x-coordinate of p, so in this case it would be -3, and substituting it into the second derivative equation. Now, the relationship between the shape of the graph and the second derivative value is a little bit harder to determine in this case. If I move p around on this left-hand side of the graph, we can see that the second derivative has a negative value. I've actually color-coded this so that anytime it's negative it'll be red and anytime it's positive it'll be blue, just to help us see what's going on. So as I move p along the curve, this value is always negative on this left-hand side. If I move to the right-hand side, we can see that all of a sudden the second derivative is in fact positive all the way along here. And obviously somewhere in the middle, in this case it's actually right on -1, which is very nice. If it's going to snap to it, which it doesn't want to, there we go. We actually see that the second derivative in this location is 0. So on the left it's negative, on the right it's positive, and in the middle it's 0. Now to work out what's going on, what I'm actually going to do is I'm just going to highlight on the graph the places where it's negative in red, so it's negative all the way along here, and the second derivative is positive all the way along here. I've color-coded that blue, and if you look at just one half of that function at a time, the left-hand side and the right-hand side, each of those looks like a bit of a parabola. This left-hand side looks like a concave down parabola, and the right-hand side looks like a concave up parabola. And in fact, this is what the second derivative is going to be classifying about the curve. If I'm at a place where the curve is concave down, I'm going to get a negative second derivative. If I'm somewhere where the curve is concave up, I'm going to get a positive second derivative. And if I'm somewhere in between those two, where it's concave down on one side and concave up on the other, I'm going to get a second derivative equal to 0. We've talked about the second derivative. If I wanted to give it a word that described what it's actually measuring, that word would be the concavity. If you don't like that word, an alternative you could use is the curvature. Okay, so if the second derivative is negative, it means that we're in a location like this one, where the graph around it is concave down. It's curving downwards. Okay, so in situations like this where it's concave down, we expect the second derivative to be less than 0, to say it's curving downwards. If we're in a situation like this where we're concave up, then we expect that the second derivative should be greater than 0. Finally, if we're in a situation like this one, where we're somewhere in between where it's concave up and concave down, we call this an inflection point. So an inflection point is somewhere where the concavity changes, where the curvature changes. It goes from being concave down to being concave up, or from concave up to concave down. And in these locations, the second derivative is always equal to 0.